Hi, I'm Sarah Witzke and I'm an application scientist here at Chemical Computing Group. Today I'm going to show you covalent docking. In covalent docking, we use virtual in situ reactions to covalently dock ligands and investigate how they bind to a target protein. Here, we can specifically define the reactive residue for covalent binding, or we can explore potential reactive sites in the receptor pocket which could participate in covalent binding. So let's get started. I'm going to open an example structure. Here we'll use 4GJ8. I'll load it in with defaults. This is a ribosomal S6 kinase with a covalently attached ligand. The alpha helices are colored red, the beta sheets are colored yellow, and the turns are blue. In between the yellow beta sheets and the red alpha helices, we find the ligand. In a minute, we'll take a closer look at the binding pocket. However, before we do that, we need to take care of common issues in raw crystal structures such as missing atoms and strain. For that, we'll use the QuickPrep tool. QuickPrep is a 3-step preparation protocol. Step 1 deals with missing atoms and protonation states. Step 2 prepares the structure for modeling with tethers and restraints. And Step 3 runs an energy refinement to relieve strain. I'll start this with defaults. Whenever a calculation is running, the top left corner of the main mode window will display what it's doing and how far it is. Let's take a closer look at QuickPrep. The first step deals with missing atoms. First, we find where are the missing atoms in the structure, and then we model them in. That could be a side chain, or it could be a longer gap in the backbone. In QuickPrep, we can do up to 10 residues in a row. We will then add in hydrogens, but we will do that by investigating protonation states, tautomeric states, and ionization states, so we end up with the most optimal hydrogen bonding network. In the second step, we prepare the structure for modeling by adding tethers to the receptor atoms. This will allow them to move a little bit, but not change the crystal structure too much. We will fix atoms that are more than 8 angstroms away from the ligand. This will save us time in the third and final step, the energy refinement. Here we will allow the structure to refine to relieve any clashes or strain. Now I've noted that the information in the top left corner has disappeared, meaning that the calculation is finished. I'll close this panel here. Let's take a closer look at the binding site. I'll use the option Side View that automatically detects the ligands and zoom in on it. I also note that the ligand has been rendered in a slightly thicker stick mode and the nearby residues in a slightly thinner line mode. I'm going to use the System Manager for further rendering. I'll open it here and attach it to the right-hand side of my Mo window. The System Manager gives me an overview of everything I've loaded in Mo, so that's the complex 4JG8. It's also split the atoms based on their type. So I have a line to deal with receptor atoms, one for solvent atoms, and one for ligand atoms. For each of the atom types, I can select or deselect them, hide or display them, change the color, how their atoms look, and how their secondary structure look. I have also got shortcuts to surfaces. Today, I'm going to change the color of the receptor carbon atoms to dark turquoise, and I'll also hide the ribbons. Let's take a closer look at the ligand here. The first thing we note is there's a covalent bond between a sulfur in the protein and a carbon in the ligand. I'll select the sulfur, and then the footer will tell me that this is cysteine 436. So in other words, this ligand is covalently attached to a cysteine on the sulfur. Mo will automatically detect and render the hydrogen bonds between the ligand and the proteins. They're shown as dotted blue lines with a cylinder on top. The longer the cylinder, the stronger the hydrogen bond. In this particular ligand, we have multiple medium-strength hydrogen bonds between the nitrile, the amide, and the hydroxyl group. There's also a solvent-mediated interaction. In the other end of the ligand, the scaffold is interacting with 2 very strong hydrogen bonds to a part of the kinase called the hinge. So this is a typical hinge binder. I'm interested in 2 other scaffolds and ligands to see how they would interact with the same protein. So for that, I'm going to do covalent docking for each of the ligands to see how they will fit if they react with the same cysteine. But before I can react with this cysteine, I need to prepare the cysteine so it's ready to accommodate a new ligand. That means I need to break this bond between the ligand and the current cysteine. I'll use the builder, this attached to the left-hand side of the Mo window. It's split into 3. Up at the top, I have options for atoms and bonds. Below, I have fragments. And down at the bottom, I have an automatic fragment scan. I'll select a bond by pressing right in the middle of it. And then I can go to the builder and use the red cross to delete this bond. If I now hide the ligand, you'll see that the cysteine has been recreated, ready to accommodate new ligands. Let's close the builder. We can now go to Compute and Dock. This opens the Unified Dock panel. Over on the left, we have all our docking scenarios. We have a general small molecule docking, template force docking based on a common substructure, docking into experimental electron density, reaction-based covalent docking, protein-protein docking, and interfaces to external tools. Now have a look while I browse through the scenarios again. What you'll note is only the middle part of the panel that changes, the rest of the panel stays the same. I'll make sure I end up on covalent docking. Now the main part of the dock panel is split into 3 sections. Up at the top, we define the receptor we are interested in and the area of interest. We can also use a database of receptors for ensemble docking. The middle part of the panel is for defining the ligands and how to place them in the pocket. The third and final step is the refinement and the scoring. So with any panel in Mo, we start at the top, fill it in, and then we have the settings that we need. So for the receptor, we're going to use the one we have in Mo, and we'll focus on the site for the ligand. For today, we won't use pharmacophore densities, but we will use ligands, so I will browse and find a database I prepared of my ligands of interest. We'll take a closer look at them in just a minute. For the reactive site, I need to define where they will react. If I move my panel here, you can see by default it's using selected atoms, so that's the cysteine. If I wasn't sure and I'm just interested to see potential binding sites, I could set this to pocket and it will investigate all the potential options for binding. I'll leave this at selected atoms. Then I need to choose the reaction that matches the chemistry I have. And here we have multiple inbuilt reactions we can use. I'll use the Michael addition. For refinement, I'll leave it on rigid receptor, but I'll turn down the number of poses to 10 and to 2 in the interest of time. Then I'll press OK and I'll start the run. The data is being written out to a database called DocMDB, and that opens automatically in the database viewer. We'll take a closer look in that in just a minute. But in the meantime, let's take a closer look at the dock panel options. So for the receptor, we're using the one in Mo, and you will note that I'm using both the receptor and the solvent. This way I'll see if any of my ligands are interacting with the solvent atoms. If I only want to focus on the receptor and exclude solvents, I could use receptor atoms instead. The site is where the current ligand is, and the ligands are my database. I'll use the gear wheel that gives me an option to browse the database of the ligands. So here are the 2 ligands that I'm interested in. On the right-hand side of the ligands, they're the same and they're very similar to my current ligand. So I have an amide, I have an alpha-beta unsaturation, and I have a nitrile. However, on the left-hand side, their scaffold differs. The first ligand is relatively short and it has an indosol scaffold. The second ligand has a slightly different and longer scaffold. I'm interested to see if they react with the same cysteine, how would they interact with the hinge? Now the reaction to modify these ligands need to match my ligands here. In this case, I have an alpha-beta unsaturated carbonyl in each ligand that I'm going to use. Let's close this database and have a look at the reaction. So the reaction is the Michael addition reaction. We have more than 20 built-in default reactions in Mo. They're all written in a standard 2D sketcher and saved in an RxN format. You can modify these reactions or you can use in-house ones. The reaction is always defined in the same way. Component 1 matches the protein, so that's our cysteine. Component 2 matches our ligand, in our case that's the alpha-beta unsaturated carbonyl, and then component number 3 is the final product. In our case, the sulfur is using a nucleophile addition to the double bond, opening it up. Our refinement was rigid receptor. Here we could have used induced fit, which would have allowed the protein side chain some flexibility in the final refinement stage. The poses are scored with our generalized Born implicit solvent scoring functions, which we have tested and validated for docking purposes. I've noticed that the information in the top left corner has disappeared, meaning that the docking run is finished, and we can have a look at the output database. Here's the output database. It's open up in our database viewer, which is the second major window type in Mo. You'll note it's a lot like a spreadsheet, rows and columns of numbers, but if I drag and expand, you can see it also holds molecules. So here we have the ligand dock pose and the receptor. It's also the main entry point for all our cheminformatics and QSAR tools. Now the data we get out are the 2 best poses for ligand number 1 and the 2 best poses for ligand number 2. I also have S, which is the final docking score. That number we want to be as negative as possible, indicating a stronger binding affinity. In the rest of the database, I have several energy scores for each of the steps in the docking run. And I have PLIF, which is protein-ligand interaction fingerprints that you can use for statistics on how the ligand and protein interacts. I like to have a closer look at my final poses. And for that, I'll use the File and Browse option. This opens the database browser. The database browser goes through each entry at a time in the database viewer, displaying the ligand in 2D and displaying the complex in the main Mo window in 3D. I'll move the browser up here and I'll change so that I browse the complex, and I'll side view in on the binding side, and I'll use the option None to add the final docking score. This way I can keep track of the docking score both in the browser and in the top left corner of the Mo window. So here, if we look in the 2D view, we see the first ligand, and we see that it's covalently attached to the cysteine 436. We see the same thing in the 3D window. We have the covalent bond between the ligand and the cysteine, and we open the double bond. I'll have a look at the scaffold here. And I note that the indisol scaffold is placed very similar to our co-crystallized ligand and is interacting very strongly with the hinge. Let's have a look at the other pose of the same ligand. We have a slightly different position on the R groups on the right-hand side of the ligand, but the scaffold is still interacting with the hinge. Let's have a look at the second ligand. This is the one where the scaffold is slightly different and longer. In this case, I note that the carbonyl in the scaffold is still interacting with the hinge, but I only have 1 hydrogen bond. Let's look at the second pose for the same ligand. Again, very similar. I do have interaction with the hinge, but only with 1 hydrogen bond. If I'm interested in targeting the hinge, I can now choose between which of the 2 ligands are interacting in the way with the hinge that I prefer. Let's close the browser for now and re-show the original complex. So today we had a look at covalent docking. Here we can use virtual in situ reaction to covalently dock ligands to the receptor and investigate how they interact. Today we use the specific site of selected atoms, but you can also explore potential reactive sites in the receptor pocket to see which of them could participate in covalent binding. I hope you learned a lot today. If you have any questions, please reach out to me at support@chemcom.com.